Okay, so here's what we were talking about last time. We were talking about graphs and level sets, different ways to visualize functions, multivariable functions. And it's important to start this conversation. Let me say it again. I know I said it a bunch of times last time, but you've got to make sure to sort of separate in your mind the distinct ideas of what is a function and what is the graph of a function, right? They're not the same thing. It's just simply not true to say that, if you're looking at a function, then the graph is the picture that helps you understand that function. It's just not true, right? So, for example, here's a multivariable function, right? Function from R2 to R1. Got a nice formula for it. And we can draw the level sets and we can draw the graph. They give us different kinds of information. Both of these pictures are flawed. Right? Let me pick on level sets first because it's at the top. I didn't draw all the level sets. I've only drawn some of the level sets. I can't draw all of them. If I drew all of them, the entire page would just be solid pencil lead, which doesn't help me at all. Right? So you can only make some of the level sets, and therefore there's gaps. Right? So I don't really have in this picture any explicit information about what's going on in this sort of gap area in there. That's a shortcoming. Okay. But hey, the graph has a pretty nasty shortcoming as well. Now, it's tempting to say, but come on, the graph shows everything about the function. For every input value, there's a corresponding output value. All those points are on the graph. True, but I didn't draw that, did I? Right? I drew that curve of what you might call the horizon line to this graph, and then I drew this little circle to help you visualize kind of the three-dimensionality of it. But I didn't draw anything at all here or there or there. So a drawing of the graph is also wildly short on details. And I suppose you could say, well, yeah, but I could 3D print, right? Or make out of paper mache or whatever, an actual graph. And I suppose you could, but realistically, it's hard to fit three-dimensional pictures into two-dimensional books or exam packets, right? So it's just not realistic. So anyway, be aware of the difference. Think about that difference. So we're going to move on now. I did a bunch of other stuff, various other examples. And by the way, everybody's a big fan of graphs already. You come relying even on graphs, right? But I don't want you to continue to rely on graphs. I feel the need to pull students away from sort of dependence, using graphs as a kind of a crutch. Oh, this is the only way I want to think about functions. So I have some sales pitches for level sets. One is you can always turn a graph into a level set. So level sets have this a little bit more, I don't want to say universality, but they can be used more often. They're a little bit more broad in their application for this reason, right? So when we understand the calculus of level sets, this is a way to help us understand graphs. Anytime you have a graph that you want to understand, view it as a level set, as you always will be able to, and then use the calculus of level sets. So we talked about that. Here's the sort of the broad idea, and here's a specific idea. If you want to understand this graph, reinterpret it as a level set. And here, look, it is. It is literally a level set of this new function. And the calculus of level sets of this function will help you understand this graph of that function. Okay. It doesn't go the other way around, though. Not every level set's a graph. Again, we failed the vertical line test. Easy example. So this is a win for level sets. That's where we left off last time. Here's another pitch. I like to say that level sets are dimensionally simpler than graphs. And I think this is a really big deal. We've already kind of hinted around at this point. So let's look, for example, at this function here, function of 2 inputs, 1 output. Here's the graph. Here's some level sets. And notice the level sets, it's a 2-dimensional picture. It's just easier to draw a 2-dimensional picture, right? The graph is a three-dimensional thing that I'm trying to kind of con you into believing that I drew by drawing actually a sort of two-dimensional figure that I argue is related to the three-dimensional thing. I didn't really draw the three-dimensional thing. I have two-dimensional paper. I have a good old, plain old-fashioned one-dimensional line drawing, I'm going to say pencil, stylus, whatever. So dimensionally, much easier to understand from a point of view of level sets. And you might say, look, that's a sacrifice I'm willing to make. Okay, well, what about for a function with 3 input variables? You can still, kind of, sort of fake your way into suggesting you've drawn some level sets. And certainly we've drawn a picture that gives a geometric representation of those level sets. Yes. Imperfect though it is. But you lose on the graphs, right? Can't do it. There's 3 input variables. There's 1 output variable. That's 4 variables, and we just can't do. You cannot draw. You can't even pretend. You can't even fool me into thinking that you kind of, sort of drew a graph that is a 4-dimensional thing that lives in a 4-dimensional world. We just can't. It's off the table. Okay, so being what I'll call dimensionally frugal, big win, right? And that's another win for level sets. Okay, so so we're done with all that 13.1 and 13.2 business now, and I'm going to move on to 13.3. So this is about limits. Limits is a very, very important topic. Let's talk about single variable calculus. Real quick, just for kind of context, a little cultural note. I propose that limits are the cornerstone idea of calculus. Right? I make a deliberately strong statement there. And the reason I say this is because if you think about it, let's think about, the 2 big ideas that people think of when they think of calculus are derivatives and integrals. Okay, well, wait a second. Yeah, but derivatives, what do you need to be able to define a derivative? Well, it's limits. Right? Derivative is defined fundamentally as a limit. Okay, yeah, but what about integrals? Integrals are a very different thing. How are integrals defined? Well, they're defined with Riemann sums, which are limits, right? So both of the big, on the marquee out front of the show concepts of calculus are defined with limits. So this is the cornerstone notion of calculus. So anyway, kind of a big deal. By the way, let me give you all a reminder. I've pitched this before, but I have on my YouTube channel a playlist called Miscellaneous Topics, and those videos serves various different purposes. One of them is to give students a reference if, in certain key cases of concepts that I think students really ought to be familiar with and very often aren't. I want them to have a reference that I can point to. Okay, here's the, real quick crash course, very important, commonly misunderstood concepts of, whatever. And I have one on limits, so I'd encourage you to take a look at that if you don't feel like you're not really strong with limits. Anyway, FYI. Okay, so in single variable calculus, a point of view that you might recall is that, one of the requirements is that when you approach from one side versus if you approach from the other side, right, the limit that you get from approaching from the left, the limit that you get by approaching from the right, these two have to be the same. If these were to not be the same, well, then the limit doesn't exist. Right? If they're different, then there is no such thing as the limit. Right? Okay. So we're going to pretty much steal that idea and use that as a way of understanding multivariable limits. Same thing. If I want to talk about approaching some point here in a domain, let's suppose I have a function of 2 variables, x and y. If I want to talk about the limit of the function as I approach that point, well, likewise, I need it to be the case that no matter how I approach that point, no matter which of these various, deliberately drawing some weirdo paths that I might take to approach that point, I need those limits to all be the same. If any 2 are different, then something is wildly weird about the function in the vicinity of that point, and I would not want to say that we have a limit here. Okay, now students very often don't like this picture, really, or this picture. So let me show you something more familiar. Here's the more familiar perspective on single variable limits. Right? We draw the graph because we can, and because it's familiar, right? And so this is the kind of picture you often see. You know, as you approach some point A, we need the value of the function, you know, from each direction to approach this same, you know, value L here that we'll call the limit. And that's a very satisfying picture. Graphs are great when you can draw them, right? When they are not entirely inaccessible, they're super. But here's what happens if I try to take this picture, this luxurious, opulent graph picture of limits, and extend that to a multivariable context. Here's what I find myself trying to draw, right? So here's a picture, here's a graph I've drawn of a multivariable function. I've got a function from R2 to R1. Forgive me, loosely speaking, I'm going to say R2 is kind of this down here, and R1 is kind of, you know, I mean, again, it's a way of thinking about those, but so the graph is this surface-like thing, and you can think of it as, well, look, no matter which path you approach this point in the domain, right, no matter which path you take, I need to know that what the function is doing, or you might say, you know, what happens above those curves on the graph, if you prefer, right, they have to be approaching, you know, kind of that same point, and again, we would call that the limit. And here's, now I can point out what's really, really lacking about this picture. It's another one of these head tricks that I've played on you. I didn't draw the graph, right? I totally didn't draw the graph. I drew some stuff over here that's kind of vaguely suggestive. Oh, well, I'm drawing how it curves way over there, and I'm drawing how it curves way over here, and I, you know, appeal to your imagination. Now, you think you're seeing what the surface is doing in the vicinity of this point, but you're not. I didn't draw anything over here, right? So it's a pretty bad way to understand multivariable. Correction. It's a highly flawed picture to be stuck with as a way of understanding multivariable limits. Okay, so what I want to encourage you to do is, yes, of course, try to think in these terms for intuition purposes to the extent that you can, right? I mean, again, it's even just thinking in your mind, it's geometrically challenging, right? But don't rely on being able to draw these kinds of pictures. So in the same way that, you know, looking at single variable limits again, now here we got away with it, and it was perfectly fine to draw this picture, no problem. Graph is super. But I draw just the domain here. Just the domain, like I did initially over here. Think about what's happening in the domain only. So analogous to that, in this multivariable context, what we're going to be mostly doing is drawing just the domain, right? Like I did here, drawing just the domain to understand what we're doing with the multivariable limits. Okay, so for your consideration. By the way, we kind of really do need pictures of the domain, right? Because we have to be able to talk about all these different paths along which we're going to be approaching this point that we're interested in, right? And so it helps to be able to draw what are these paths. There's more than two of them. Right here, there's only two paths. You can only approach A from the left or from the right. That's it, right? But here, there's bazillions, right? Uncountably, infinitely many different paths along which I could approach that point. Okay, so I need to be able to help represent them. Let me point out what we're not losing on this. A lot of people think, well, but then I can't see what I'm doing because I can't see the graph. I can't see what the values are doing, and isn't that kind of what the function is doing? Don't I really need to be able to see what the function's doing? Well, not really. If you think about it, when we do these calculations with limits, it's all algebra, right? We're not arguing about what limits are by using the picture as evidence. No, we do calculations with algebra. So we don't need that. And likewise, I mean, again, it's nice to be able to draw a picture and et cetera, but we're not going to be making our case for what limits are based on what the picture looks like. We're going to be doing algebra. We're going to be understanding these values algebraically. Okay. All right. So I just want to make sure everybody's got the right visual geometric perspective there. And on to an example. There's some weird stuff, by the way, that happens with limits. I am also, for the record, I am deeply editing this presentation. Limits are, it's deep water. Deep water. It's a terrible little bunny hole that you can fall down if you want to get fully into the rigor of, what is the definition of a limit and what are the most anomalous weirdo cases? Why does it matter? Oh, it's real far down, and we're not going to be able to do that in a course like Math 212. It's also completely not necessary for your purposes, right? So I'm cutting this down to what I think you really need to know. So I'm just going to go in with some examples. Starting with this one, let's see if we can, fingers crossed, compute this limit. We're approaching the origin. Now let me draw the picture. Keep in mind, as we're approaching the origin, I'm not drawing the graph. I'm drawing just the domain here, just the xy axis. We're not going to see the graph at all. Don't interpret y as being, the height in this picture as being the value of the function. It's not. Y is an input variable. This is just the domain. Okay. And here's the origin that I'm approaching. And let's think about different paths that I could take that approach this point. You're going to have a lot of different paths. We're going to start with that one there, where we approach directly from the right. But we're also going to have to consider paths where we approach like that, or maybe like this, or maybe we do a knuckleball kind of thing, whatever, right? We're going to have to consider lots of different paths. Okay. Okay, how are we going to do this? How are we going to algebraically represent moving along a certain path? Well, let me come back up to this picture here. If you think about it, a great way to represent these kinds of paths is for me to tell you where am I as a function. And if I give you position as a function, x and y as functions, then, well, that tells you where I am as I move along a path. Now, there's different ways I could tell you where you are. I could tell you x and y both as functions of some variable t. That's just a parameterization, and that gives you information. And we'd talk about, as t approaches 0, for example, or as however I choose to parameterize. 0 is a nice point to use. Or I could consider x and y both as functions of x, and then talk about x approaching, again, appropriate to the context, maybe 0. So those are both fine. Now, if you take this point of view here, if you do choose to say y is a function of x and have x go to 0, note now if y is a function of x, you've got to pass the vertical line test. And so you can do that for this curve, right? But you can't do that for this curve here. This curve does not pass the vertical line test. Y is not a function of x, so that's not an option for how to do that. Okay, so anyway, you've got options. By the way, you can have x be a function of y, if that might be convenient for whatever reason. Anyway, you're going to need to describe position as a function of a single variable. So in this case, kind of the easiest way to do it, this first example, is we're just going to view y as being a function of x. And it's an easy function of x at that. Along this path, y is just 0. So there you go. We're gonna have x approaching 0. And the formula for y is, well, it's just 0. Okay, so that being said, how do we plug that in, as it were, to this limit and make progress? Well, it's exactly what you would think. You just take this formula and you just straight up plug it in there. There's no tricky curves in that part of the problem. Just plug it right on in. Right? And again, we're understanding this multivariable limit along this path that I'm understanding with this single variable limit. And so here you go, right? So y equals 0. I get a couple of zeros there. And we have a good old Math 111L single variable calculus problem of how to compute this limit. Now, let me pause again. Don't forget, I assume in this course that you have the prerequisite. Of course, the prerequisite is Calc 2. Prerequisite of Calc 2 is Calc 1. So I'm going to assume that you are solid with limits. If you think you might not be, if you're a little I sort of glossed over that part of my Calc 1 knowledge or what have you, or maybe you just didn't have a good presentation, whatever, then it's something you definitely need to fill in. Right? So I'm going to talk through some of the little tricky details of a couple of these single variable limits as we go through here. But I can't go off and redo single variable calculus. This is a multivariable calculus course, right? So if you're a little weirded by any of this single variable limit stuff, come talk to me in office hours. Watch my YouTube lecture on limits, and then come to office hours, and we'll get it straightened out. Or pick up your old calculus book from high school, whatever. Okay. All right. So here's our single variable limit. What do we do with this one? A lot of students make the mistake of thinking, okay, well, look, x is approaching 0, so this is 0 over 0, and that's undefined. And therefore, the limit doesn't exist. Wildly wrong. Wildly. Right? X is not 0. X is approaching 0. And in fact, if you look back at the single variable definition of a limit, what this really means actually is not just that x isn't 0 yet. What it literally means is that x is not 0. But it's approaching, and other things, right? But among other things, limit as x approaches 0 means that x is disallowed from actually being 0. Right? So this is not 0 over 0. X is not 0. And what happens when you take not 0 and add 0? Well, you get that thing. So that's just x squared. I mean, y really is 0. Right? 100%. That y is 0. So on the denominator, you get x squared. In the numerator now, let's think about this carefully. I have not 0 times 0. 0. Nothing tricky about that one either. That's straight up algebra. So now what we realize what we actually have here is then this limit. And now again, a lot of students make the mistake of thinking, okay, well, isn't it kind of an indeterminate form because isn't it sort of 0 over 0? No, this is explicitly not. This is 0 divided by not 0. And again, straight up easy algebra, nothing tricky curves there. That is 0. So this is really the limit we're evaluating. We're evaluating a limit of 0. That's an easy limit. That limit is 0. Yeah.
Are you not going to consider the other paths that we talked about?
The other curves? Yeah. Oh, yeah, no, yeah. All I've done here is consider one path. Right? So, yeah, you're quite right. I got to consider all these other paths and, weirdo paths and, yeah, absolutely. So, to this question, I have no idea what the answer to this question is yet.
At this point, how do you even know that the limit exists?
I don't. No, yeah. No, we're certainly not going to assume that it exists. I've barely started on this question. Yeah, totally. And that's a great point. Okay. So, here's what I'm going to do now. I'm going to try approaching along a line like that. These are different curves. So I'm going to take a slightly different approach to this, of course. And this is, you might say this is the equation of that line. And so now again, I'm going to think of this as, well, we'll let x approach 0, and this is my formula for y. So again, plug it in. Just straight up, let's see if I can, I can't quite fit that all in there. Straight up, plug it in. Y is mx. So toss that right in there. Right? And a little bit of algebra. And notice that we can cancel the x's. Oh, by the way, are you allowed to cancel the x's? Wait a minute, you're not allowed to cancel zeros. Is everybody aware of that? You can't just cancel 0. Like if you have 0 over 0, that's an undefined thing. Are you allowed to just cancel 0? You can't cancel zeros from both sides of an equation. Are we allowed to do that? Can I cancel these x's here? Yes, absolutely. No concerns at all, because again, this tells me right here, x is explicitly disallowed from being 0. So, free and clear, cancel the common factor of x squared. Right? So, no problem. So I get this limit. And again, this is an easy limit to compute because, well, after all, this is just some constant. Right? M is constant, and therefore, this little formula, constant. Limits of constants are those constants. Okay. So, did I get the same thing? Along this curve, I got 0. And then along this curve, I got that. So let's ask the question, are these the same? They would have to be the same if I were going to claim that this limit exists. Are they the same? Nope. Right? Perfectly clear. They're not the same. I got clearly 2 different values. I mean, if you want to just go ahead and be more explicit about it, plug in m equals 1. Right? I get to pick any value of m I want. Let's let m equals 1. Now I can directly compute that formula. I get 1 divided by 2. That's a half. And a half is 100% not equal to 0. So I have 2 different values along 2 different curves. This limit does not exist. Yes?
Is there any good way to know what values to try for the limit so that we don't, end up trying out 3 different paths before we find out?
I wish there were, sadly. I suggest starting with easy, because why start with something really hard only to subsequently find out that something easy worked, right? Then you'd just be banging your head in regret, right? So, I tend to start with easy things, right? I will suggest, by the way, the following. I suggest that you not do this one. And the reason why is it's part of these, right? That the y equals 0 curve is just, it's an example of one of these with m equals 0. So why do a single line and then have to do a whole separate calculation that would have included that single line in the first place? So this was really kind of wasted time up here. The only reason I actually do this first is because I want to start with something that's explicit, something that's a single curve, kind of as a, sort of a training wheels sort of first example. But in practice, no, just go straight to the straight lines. Yeah. Okay. And by the way, then notice that, again, I don't even need that 0. I could just plug in 2 different values of m. I could plug in m equals 1 and m equals 2. Or I could plug in m equals 1 and m equals 0, which is, again, effectively equivalent to what we just did. Okay, different values on different paths. Limit does not exist. I don't have any responsibilities to check any more curves. Okay, yes?
So, what does this limit conceptually mean? So, what does it mean to send the x vector and then be close to a 0 vector?
Yeah, and so what that means is I've got let me go back to this picture, is I've got this function, right, this multivariable function, of which I like to pretend I have a graph. And in the domain here, I would like to be able to say that, I'm going to have to be a little bit vague about this because I don't want to write down the explicit definition. I would like to be able to say that the behavior of this function in the vicinity of this point in the domain, keep in mind, my inputs are in the domain, right? I would like to be able to say that in the vicinity of that point, this function is really easy to understand, and it's just all of the values in that general vicinity. They're all really close in some sense that I don't want to be precise about, really close to that value L. Yeah, that's sort of the intuition. It's really just sort of a rip-off of the intuition of this idea. Yeah. Okay, let's see another example. Here we go. Just more algebra. Starting with all the lines, right? Plug that in as usual. Algebra. Cancel a bunch of x's. Now you can't cancel all of the x's, right? This x is left over. There's three x's in the numerator, 2 in the denominator, so we do have an x left over, right? So along all lines, I get the same value of 0. So none of these are contradictory. Now, there's a landmine. We're about to step on a landmine. I want to warn everybody, please don't make the following mistake. A lot of students think, okay, well, then look, I've checked every possible direction along which I could approach the origin. We're approaching the origin here, and these lines represent every possible direction from which I could approach the origin. There's no contradiction, right? I mean, surely that's sufficient to conclude that the limit is equal to 0. And sadly, weirdly, disturbingly, not so. Keep in mind, we are responsible for checking all paths. I've only checked the straight lines. I haven't checked the spirals yet. Right? I haven't checked the parabolas yet. I haven't checked the knuckleballs. Those are hard. Right? What? And what about knuckleball spirals? Do I have to do those too? I mean, right? There's just so many different paths along which you could approach. And you might think to yourself, okay, well, come on, you're not being realistic. I mean, I can't possibly check all paths. But you got to give me the following. Hypothetically, if there were a function where if you approach along a spiral, you get a different value, right? Then if you approached along a straight line, you would want to disavow any suggestion of that maybe there's a limit there, right? I mean, because something super weird is going on. Okay, so the next thought is to think, well, yeah, but come on, is it possible? Could it, I mean, if you've checked along all possible straight lines, and if along all straight lines you always get the same value, doesn't that kind of encompass all different directions, sort of? And it's very tempting, and you'd really think this is true, but also not true. And this is deep. This is weird. One of the big takeaways I want you to get from today's talk is multivariable functions, by having a multivariable domain, have enough elbow room that gives them the capability to be weird in ways that single variable functions just can't emulate. So your experience with single variable simplicity is not sufficient to understand multivariable functions. And did I see a hand, by the way, somewhere? Is everybody good? Okay. So let me show you what can go wrong, and this is super weird. Well, I got a little ahead of myself. Let me finish this example before I do the super weird one. Let's approach along parabolas. Just being open-minded at the seemingly unlikely possibility that maybe we'll get a different answer than the obvious straight line tangent to this that we've already checked. Right? Well, here you go. Let's check this and plug that in, as appropriate. Plug it in for y. Do the algebra, yada, yada, yada. And look, we got 0 again. So again, we didn't get contradictions. But we still cannot conclude anything, because I haven't checked the spiral knuckleballs yet. And it seems really sort of unnecessarily careful, but now check out this example. Now this example is not that scary looking, right? Harmless, seemingly harmless. It's a rational function. It's just a ratio of polynomials. There's no cosines or logs or inverse cotangents or anything like that. It seems like an innocent little function. And I'm going to let you guys do the algebra on this, but here's how it works out. If you look along the straight lines, 0, all of them. If you check along all of these parabolas, still 0, all of them. And yet, if you check along these cubics, make sure you can do the algebra, you don't get 0. And it's hair-tearingly unintuitive, non-intuitive. And yet, here we are. Right? So I think it's worth taking a little time to chew on and digest what in the world just happened here. It feels like I approached this point along all possible directions, and shouldn't that tell the whole story? Apparently not. Right? If you sort of bank it in, bend it into the origin here, you get a not 0. Yes?
Do
Do you only have to keep checking for a contradiction if your first limits are equal to 0?
You only have to keep checking if you don't get a contradiction. So by being 0, there's no contradiction. Now, if those limits were all 6, still not a contradiction, right? But if in this list of limits that you compute along the various different paths, if you get any 2 of them that are different, then you got a contradiction and you drop your pencil and walk away. Game over, right? But until you get 2 answers that are different, you don't know anything. Because you can't exclude the possibility that, I don't know, maybe x to the 17th. Right? Right, so super weird. Yeah.
Yeah, is there any way you could, like, geometrically?
No, it's very hard. It's very hard. The book has a picture of either this function or something very similar to it, and I don't remember exactly which one. But again, it's a picture in a book, and so it's a 2-dimensional picture of something, a graph, which is intrinsically in a 3-dimensional world, and it's not a very good picture, to be frank. And it's computer generated, so don't even try to draw. I will say, if you really would like to see a 3-dimensional model of a function that I can persuasively argue to you, the limit does this weird thing. I actually can do that in my office hours, but I can't do it in lecture. So come on by office hours, and I'll be happy to show you such an example. And you had a question? Whoops, sorry. Can't hit a button. Was there another hand somewhere? Yes.
So how do you know how far to go?
Yeah, no. Sadly, there is no answer to that question. This is not a. You have to do, sufficient. You have to, put in a noble effort. I wish that were the case, right? You have to check all curves, all of them, and of course you can't. Right? So I am not going to be giving you a method by which you can always answer questions about limits. Sometimes we just don't know. Yes.
So then, could you argue that a limit never exists? Because there's always some curve that you're not checking.
It's a great question, and I'm about to answer that question. Yeah. So concluding that a limit exists seems implausible for exactly that reason. So let me show you how you can do it sometimes. And again, it's only sometimes. So the idea is to use polar coordinates. And I know y'all may not all have seen polar coordinates. If you haven't seen polar coordinates, no problem. Here's a quick introduction to polar coordinates. It's just another way of describing where you are in the plane. One way to describe where you are is by looking at these values, x and y. And it's very convenient, a lot of neat features. But another perfectly acceptable way to describe where you are is to tell me what is that angle, and then that angle defining as it does a direction away from the origin, how far should I go in that direction? And we define these as theta and r. And you give me an r and a theta, and that tells me where I am in the xy plane. And it's easy to write down certain relationships, right? Trig. Hope y'all all remember your trig. Hope you're all good and solid, proficient with your trig. Another thing that if you aren't, be sure to polish that off and get good at that. Certain other relationships you can write down. Right? Very neat. And that's really all we need to know about polar coordinates for what I'm about to do here. I'm going to make the observation that with this setup, if I want to talk about limit as x approaches the origin, I claim that this is equivalent to taking a limit as the polar coordinate r approaches 0. Now, I think this is a pretty easy pitch. I mean, any curve, here, let me get weirder, knuckleball spiral though it may be, if it approaches 0, then the polar coordinate r is approaching 0. I mean, right? I mean, it just has to. And then likewise, if you have some curve where the distance to the origin is approaching 0, there's no way to get out of this, but if the distance to the origin is approaching 0, then that curve itself is approaching the origin. Again, it's the same concept, it's the same thing, right? And what's beautiful about this observation is that this is a way of, in this case, sometimes this happens to work, if you are looking at a limit as you are approaching the origin. It's got to be the origin. Then we can turn a multivariable limit into a good old, plain old, single variable limit. And single variable limits, again, we all know lots of stuff about. We have lots of tools, and et cetera. Right? So it's a very powerful trick. And let me show you an example of this in practice. Let's go back to this function that we were looking at before. And, we tried the straight lines. And I think we tried the parabolas, right? And then we were just kind of threw up our hands like, well, what am I going to just sit here and keep checking higher and higher powers of x? That's an endless game, right? You'll never catch the bunny, right? It goes on forever, right? So, okay, let's do this instead. Let's capitalize on the facts that we're approaching the origin. Again, I emphasize, this only works if you're approaching the origin, right? That allows me to rewrite a multivariable limit as a single variable limit, in exchange for which now everywhere I see an x, I've got to convert that into polar coordinates too. Everywhere I see a y, here, let me just do it like this. Everywhere I see a y, I've got to convert that into polar coordinates. And then instead of doing that down here with these, let me make a smart alecky observation that x squared plus y squared. I mean, I could write that down in terms of cosines and sines, but it's always r squared. So let's just save ourselves some trig and rewrite it as such. Yes?
Wait, why wouldn't it work for non-origin?
Yeah, it's just not the so. For example, let's suppose I wanted to talk about some point over here where r is equal to 3. Let's say and let's call this point A is approaching A the same as letting R approach 3? Well, sadly, no, because I can think of plenty of curves where R approaches 3, but I don't approach A. So, for example, a curve like that. R approaches 3. X does not approach A. So these limits are simply not the same thing anymore. Yeah. So 0 is sort of unique. The origin is sort of unique in this. Yeah. Okay, so we've got a good news, bad news situation here. The good news is we've gotten rid of the multivariable limit. The bad news is we've introduced a bunch of trig. Right? So that's not necessarily good news. And how do we deal with this? By the way, let me come back over here real quick. Give me a second, real quick. I get to say R is approaching. Let me get this back to. Let's see here. We're approaching the origin. Forget about this. R is approaching 0 again. I know what R is doing. R is approaching 0. What do I know about theta? The answer is nothing. You cannot make assumptions about theta. Students tend to like to say, so I'm just going to assume theta is 0. That would be suggesting that you're restricting your attention to just this line. You're no longer checking all possible curves, right? So you can make no assumptions about theta. Now let me say that a little bit more vividly, I think. Think of theta as not only something that you can't control, but something that's kind of actively working against you, right? Because it certainly could be. You're certainly responsible for whatever's the nastiest thing that little jerk could possibly come up with to foil your plans, right? If theta can do something annoying, you have to worry about that because it's allowed to do that annoying thing, right? So we've got to look at this expression here now and understand this limit with the understanding that theta could be going wild. And it seems like we couldn't possibly. Beautifully, though, notice a lot of R's cancel. And we end up with this expression, and I have this factor times that factor, and a couple of neat coincidences sort of combine. For one thing, this expression, even though I have no control over theta, I know that expression it's only so crazy it can get. I mean, this is clearly between -2 and 2. There's no way. that expression can be outside of between -2 and 2. And furthermore, this fenced-in, bounded little devil here is getting multiplied by something that's clearly approaching 0. So, squeeze theorem, this limit's equal to 0. Yeah? Pretty good? So that's the trick. It's very clever. This is how you can sometimes prove that limits occasionally. Actually, you can conclude that they do exist. But we have limited tools along those lines. Here's another example of how to use polar, by the way. If you play the same trick, convert rectangular to a single variable polar limit like that, plug in the calculus, all the r's cancel, details for you guys, right? You end up with this thing here to take a limit of as r approaches 0. And I remind you, r is approaching 0, but theta is a rabid dog running around in circles. I don't know. It could be doing all sorts of crazy things. And what is this limit with no control known over theta? Oh, well, it's clearly going to take different values. Right? In fact, you don't even have to have theta doing anything crazy. You could just say pick theta equals 0, and now subsequently pick theta equals pi over 2. You get different values. Okay. So this limit does not exist. Yeah.
Why do we only consider r approaching to 0? Why don't we consider theta approaching to 0?
Because geometrically there's no argument such as this. So we critically need the observation that curves approaching the origin force this arc distance to approach 0. And just geometrically, that's you make an argument like that about theta, it just doesn't work. Yeah. Okay, so last thing I want to say is about continuity. So I hope you all remember continuity from single variable calculus. It's again one of these ideas that's seemingly kind of intuitive, but a little bit more delicate than you might expect at first glance. Right? Here's the definition. Here is an adapted adaptation of that single variable definition, adapted to the multivariable context. So let me just go straight to the multivariable version. For a function to be continuous at a point, I need all 3 items on this checklist to work. I need the function to be defined at that point. I need the limit to exist, and I need for those 2 things to equal. Yeah? Okay. And you can draw pictures of, why this is reasonable. The motivation for this is the same in a multivariable context as it is in a single variable context. The idea of continuity is you can't have a hole at that point, and you also don't want something too weird happening near that point, and you want there to be consistency between those two things. So, turns out this is a lovely tool for computing multivariable limits. Now, it doesn't seem like it would be, because, after all, in order to use continuity, I would have to already know the value of the limit, right? So, if I need to know the limit to ascertain continuity, how could knowing continuity help me compute the limit? This is a circularity problem. Does everybody see the circularity problem? Okay. It turns out this is not quite circular, because it turns out we already know bunches and bunches of functions are continuous. And how do we know that bunches of functions are continuous? Well, because mathematicians who have come before us have already gone to the trouble of proving, at great inconvenience, that they are. And so we just get to piggyback off of that work. And it's extremely convenient. So, for example, polynomials, all continuous. Feel free to use at your convenience, right? You don't have to, in this course or, probably any further course, need to prove that polynomials are continuous. They are continuous, yes.
So if you know a function is differentiable, that's automatically...
Yeah, that's another true fact. Every differentiable function is continuous. Absolutely. Another handy one. Absolutely. And so how do I use this? How do I use the fact that, I know polynomials are continuous, right? Well, I use it as follows. If I'm ever asked to compute a limit of a polynomial, I say, I know the polynomial is continuous, so I already know all 3 of these statements are true, among which I know that this statement is true, and that tells me that I can compute that limit simply by, and this feels real wrong, this feels like we're massively cheating. But I could just take that thing and plug it into there as prescribed by this formula, and boom, there is the value of the limit. So the plug-in, plug and chug approach to computing limits, which is wildly inappropriate on first principles, actually works for continuous functions. If you know your function's continuous, it's easy. Right? This is awesome. Now, don't take, a lot of students say, okay, you know what? This is my brand new favorite way to compute limits. I'm just going to do this all the time. Oh, no. No. You have to know in advance that the function actually is continuous. If you just plug in, and if the function's not continuous, and if you don't say that you're using the fact that it's continuous, then it looks like you just have a wildly naive understanding of limits. So you can't do that at all. Yes.
But do you just prove the function is continuous?
Well, no. The big point is that we don't have to, right? So with polynomials, I can just cite this theorem. They're continuous, and the list goes on: exponentials, logs, trig functions. Got to clarify one thing. That y'all all know that tangent, for example, is not continuous. It's got a violent discontinuity in various places, right? But what it is continuous everywhere it's defined, right? It does have massive discontinuities. It's also not defined at those massive discontinuities, right? So keeping that in mind, and by the way, whenever you add continuous functions, the sum is continuous. When you multiply, divide, again, you got to worry about don't divide by 0 because then it wouldn't be defined, right? But pretty much anything that you can do to combine continuous functions, the result will be continuous where it's defined. Yeah.
And then, if we're calculating it, like if we calculate f of a, we're going to find out that it's not defined towards the end anyway.
Yeah, that's right. So that's what I'm going to do with this function here, for example. Now, this looks like a nightmarishly difficult problem, but this is actually marshmallow freebie almost problem. All you have to do is make the observation that first, this function is a combination of known continuous functions. Known, right, per the theorem. So it follows that this function here is continuous where it's defined. So all you have to do to justify use of continuity here is just confirm that this is actually defined at the point that you're interested in. So I'm interested in this point 3, 1. Take that point 3, 1, toss it on in there. There's no problems. Tangent's not defined some places, but it is defined there. Log's not defined in some places, but it is defined there. So this function's continuous. Because it's continuous, the value that I get is the value of the limit. Okay. All right, good stopping point for today. We just finished 13.3. We'll pick up with multivariable derivatives on Friday. Y'all have a good day. See you later.